Hello everybody, it's a pleasure to be a panelist for this webinar hosted by the Institute of Physics Publishing and in particular the journal Plasma Physics and Control Fusion, or PPCF. My name is Jonathan Graves and I'm Editor-in-Chief of PPCF. This webinar is the second of a series of webinars that we are holding on important topics for the plasma physics community. The topic today is negative triangularity tokamaks, a power plant plasma solution for the core to the edge. As you'll see, it offers potential solutions to some of the biggest concerns into safe and reliable energy generation for tokamaks. So I'd like now to hand over to the chair for this webinar, Justin Ball from EPFL in Switzerland.
Thanks, John. I'm excited to be here for, again, this PPCF webinar on negative triangularity. The format and the schedule you should see on your screen. So we have a set of 5 excellent speakers who will each be giving 15-minute talks on different topics related to negative triangularity. After each talk, we'll have a short amount of time for question and answers. So you should see through the webinar system a text box that allows you to submit questions. So feel free to submit questions at any time throughout the talk. And then when it concludes, we'll assemble the questions and ask the speaker some of them. So after these five presentations, we'll conclude with a panel discussion with all of the speakers. And so if you have more general questions about negative triangularity, this is a good opportunity to ask the panel. So again, you can submit them through the text box. This is everything from my side. So without further ado, our first speaker for today is Oak Nelson. So Oak is a research scientist at Columbia University in New York City. He works closely with the D3D tokamak in San Diego, doing experiments on negative triangularity, as well as looking into the physics of power exhaust, as well as the H-mode pedestal. So Oak, whenever you're ready, feel free to begin.
Great, thank you so much. So it's my pleasure to be here today to talk to you a little bit about lessons we've learned from the D3D negative triangularity campaigns, and also touch briefly on some exciting new results from the mass tokamak as well. The work I'm presenting today is on behalf of a very large amount of people, so please see the associated papers for due credit where credit is due. Great, so I thought I'd start this webinar with just a little bit of an introduction to what negative triangularity is. In principle, negative triangularity is just a simple shape change. We in the tokamak community have long been studying configurations that look like this, which is a positive triangularity or conventional configuration. This is characterized by a parameter delta is greater than 0, where delta is a ratio of the x points and the center of the tokamak. So if the center of the tokamak is farther away from the main core than the x points are, then we have a delta greater than 0. This is a positive triangularity conventional configuration. On the flip side, if you then pull the x points of this plasma farther away from the main part of the tokamak, such that they're farther away from the center than the magnetic axis, you get delta less than 0. And if delta is sufficiently negative, such that delta is less than some critical delta, which we'll talk about later, we enter the negative triangularity regime, which has all these great properties that you'll hear about during this webinar. So this is the main distinction that we're talking about throughout today's talks. And these sort of subplasmas were actually very, they're not incredibly new. They were first explored in the 70s and 80s, but they were mostly abandoned after being predicted to not have access to second stability, which is something that we thought we needed to achieve reactor relevant conditions. However, on TCV, which you'll hear about in a bit, there were observations in the early 2000s of a 2 times improvement in confinement compared to positive triangularity plasmas when you went to this negative triangularity regime, which then let you achieve reactor relevant conditions in a negative triangularity sense. Since then, there have been a lot of different experiments on various machines. I will be talking about primarily experiments on the D3D tokamak that were conducted during a month-long armor campaign, which allowed for high power diverted operation and a large increase in the amount of negative triangularity data. That sort of configuration is shown here for the D3D machine. We have access to a lot of different shapes on D3D, and the main one that we've been looking at is this campaign shape, which is a very strongly negative triangularity shaped plasma with a X point here sitting right above a chunk of armor, which protects our machine and diagnostics from the heat flux coming from the plasma. And in general, negative triangularity offers quite a nice alternative path to a tokamak fusion power plant. It has several distinct advantages over positive triangularity, these being mostly in the power handling sense. So we have a lower separatrix power and a larger diverter radius, both of which allow you to better handle the power coming out of your device. You'll see in a moment that there is robust edge stability. There are no ELMs by design. ELMs are edge localized modes that would be very bad for a reactor, and negative triangularity eliminates them completely from the get-go. Like I said on the TCV results, and you'll see later in D3D as well, there's reduced turbulent transport in the core, which is good for core confinement. And there's also the access to high Greenwald fractions, which let you get to very high densities, potentially letting you optimize your situation differently and be more compatible with impurity seeking. There are some potential disadvantages. Mostly these are due to the smaller body of data that negative triangularity has compared to positive triangularity. So there's more uncertain confinement extrapolations, potentially more challenging vertical control, although there are solutions to this that have recently been published, potentially poor n=1 stability, but on D3D we do not see this much of an issue. And then of course there are engineering risks to assess, which we'll talk about at the very end. And in sum, this is potentially an alternative path towards an FPP. If you think about most of the fusion research going down a particular line, there may be alternative paths such as negative triangularity that we haven't studied quite as much that offer a bit of the same promise. So with that as introduction, I'll turn to D3D results now. One of the very cool things we saw about the D3D campaign is that it allows us to have simultaneous access to all these reactor relevant conditions. So here I'm plotting several conditions that are important for reactors. This is H98, normalized confinement, beta N, the normalized pressure, Q95, the safety factor, and access to all three of these sort of criteria at the same time was achieved very regularly on D3D, as you can see in these database plots in the bottom here, which show, for example, normalized confinement and the normalized pressure as a function of the D3D database, the D3D ELM-free database. And what's important to note here, not only will we be able to access these high confinement regimes, but the negative triangularity plasmas are not necessarily a monolith. So far, negative triangularity plasmas have been very new in research, but there are potentially many advanced regimes that should be studied, which would allow you to optimize in this space even further. Another interesting thing that we see on D3D is that as you increase negative triangularity, so going from 0 to -0.6 over here, the actual maximum H98, the normalized confinement that we were able to achieve, was increasing. And so this is a good sign that there's potential more room for optimization, even at very strong negative triangularity. Another cool thing from the D3D campaigns is the ability to access Greenwald fractions above 1. In ohmic plasmas, we were only able to get Greenwald fraction of 1. But as we are adding neutral beam power, we actually were able to increase this density fraction up to a Greenwald fraction of 2, with a Greenwald around 1 at the pedestal top. And so you can see that in these traces here. This is a function of time. We have power, normalized pressure, and the Greenwald fraction. And as you're adding power in this blue case, we're able to take that Greenwald fraction well above this Greenwald fraction of 1, which is thought of traditionally as a limit, into Greenwald fraction of 2 regime. And this is one experiment, and there's lots more to do to optimize here. But this speaks towards the ability to get to higher densities in negative triangularity plasmas than was typically possible in positive triangularity counterparts. If we're looking at profiles of negative triangularity, they are very distinct from what we would typically see in positive triangularity, both in L mode and in H mode, which are two confinement regimes that people typically operate in positive triangularity regimes. In this set of profiles, these are from 3 matched discharges on the D3D machine that have various global parameters matched. And you can see L mode plasmas are very flat, whereas the PTH mode is characterized by the traditional pedestal, which allows you to get to steep pressures right inside the core region. In the negative triangularity ELM-free case, in contrast, is a very small pedestal, something very steep and small near the edge, but then quickly flattens out compared to the H mode pedestal, and is not able to achieve this main pressure gradient. However, the NT gradient continues to grow throughout the core, which actually allows these two cases to have a total volume average pressure that is identical. In this plot, I'm only plotting the outer 40% of the plasma. The core plasma actually catches up. And so this is signs that negative triangularity is transferring some of the burden of accessing fusion relevant conditions from this H mode pedestal to the core plasma, which is good because the H mode pedestal also comes with ELMs, which we mentioned earlier are very bad for a reactor regime. In negative triangularity, these ELMs are completely suppressed, and they're suppressed with just a simple shape change. So in this plot here, this is one discharge from the D3D data set where we are scanning the triangularity up top here as a function of time from very negative to less negative. And this is done at constant power, which is typically needed to get into an H-mode regime. What you'll see looking at the D alpha trace here, which is a signature of ELMs going into the scrape-off layer and producing light, is that in the lower triangularity, you have these big spikes of D alpha, these big ELMs, which correlate to Q, which is heat flux on the outer strike point, big spikes of heat flux, which is something that we want to avoid. At less or more negative triangularity here in the blue, we actually enter an ELM-free regime where these giant spikes in D alpha are completely suppressed, and the average or the peak heat flux is also reduced compared to the peak ELM limit. And so this is reduction or the elimination of ELMs with respect to just the shape. And so what we can actually do is look at every single time slice on the D3D data set and do the same sort of ELMing analysis. And that's shown in the figure here. So this figure shows every 20 milliseconds across almost 900 discharges in D3D. This includes disruptions, this includes transient events. Every single 20 millisecond time slice is encountered in this data set. And what you'll notice very clearly is that at lower triangularity, something below this critical delta I mentioned earlier, we're able to access an ELMI regime, which is this ELMI H mode. However, at more strong negative triangularity, so negative triangularity of 0.2, 0.4, 0.6, we transition to an ELM-free regime, which does not have any ELMs whatsoever in this space. There is a small dithery regime here, which is very interesting. It's reminiscent of limit cycle oscillations from H mode transitions, but this still has a reduced peak heat flux compared to type 1 ELMI H mode, which is ultimately what matters for a reactor. So to understand why this ELM-free scenario exists, we can look at the ballooning stability in the edge region. This is a set of modeled discharges, which scan from positive triangularity in blue to negative triangularity in red. I'm plotting the outside 15% of the plasma radius in both of these plots here. In plot B, I've just assumed an H mode-like pressure gradient. And so what you can see that here, this dotted line is the pressure gradient in an equilibrium, which has a big spike in the edge. This is your H mode pedestal. And the solid lines are stability limits for an MHD mode called the infinite end ballooning mode. For positive triangularity discharges, there is a contour here and a contour here, but there is no contour in this middle regime, meaning there is no unstable regime or no unstable region in this part of the plasma, allowing the H mode pressure gradient to grow up. Conversely, for negative triangularity, these stability contours traverse the whole outside of the plasma, meaning that this part of the plasma here, where I've plotted the equilibrium gradient crossing these stability limits, is actually unstable and unphysical. This could never happen. In order to stabilize this effect, we actually have to reduce the pressure gradient in negative triangularity plasmas. So you'll see that here as a reduced alpha, a reduced normalized pressure gradient for the equilibrium in negative triangularity plasmas, such that it does not cross these stability limits. And that actually pushes your H mode pedestal down below where the ELMI limit would typically occur. We can then apply this theory to the entire D3D data set, and you end up with a plot that looks like this. So this first stability limit is that lower stability bound that I just plotted on the previous slide. And as a function of pedestal pressure and a distance to the stability limit here, we can plot the entire D3D data set again over these two axes. ELMI H mode, we see that we're well above the first stability limit in these high pressure regimes. But in negative triangularity plasmas, we're well below the first stability limit, limited by that first stability limit, which is preventing us from growing up into the ELMI H mode regime. So this fundamental shape change leads to a fundamental change in the ballooning stability, which then prevents you from going into an ELMI regime, which is great news for a reactor. I'll say that this is still not the end of the story. You'll notice that there's a lot of variation in pedestal pressure and the distance to stability in this plot. And so there's a lot more going on in this picture that we still need to figure out. But on the whole, negative triangularity compares well to other ELM-free regimes. And that can be seen here. I'll skim through this very quickly. But this is negative triangularity compared to a lot of different other regimes with criteria for a reactor on the left-hand side. You'll notice a lot of green blocks in the negative triangularity column. Actually, this is data from 2021. And if you added the new 2023 data, it looks something like this. We've made a lot of really rapid progress towards these reactor relevant conditions in negative triangularity that is still overcompensating, or it's very competitive with regimes that are trying other strategies. One thing that we can do with the D3D data set then is to try to fit a scaling to it to figure out how these negative triangularity plasmas will scale in confinement towards a reactor. And that's shown here where we're calculating the measured and predicted tau thermal energy confinement times for two different scaling laws. And in both these cases, the D3D data set is overlaid in black, and you can see that it scales greater than 1 times, which suggests that we're scaling at least as well as H-mode, but potentially better. And there are more details in this paper if you'd like to find out more about the conditions for these scaling confinements. So at the very end of this presentation, I wanted to turn to some new exciting results from MAST, just to put some mention here. Very recently, we were able to achieve negative triangularity results in MAST-U for the first time. And so this is a picture of what that discharge looks like. And as a function of time, you'll note that we have, again, constant power, constant IP, and constant density. But the delta, the triangularity, is slowly scanning down from a positive number towards a negative number. At the end of this discharge, we'll see that the ELMs, which are plotted down here in plot F, disappear, and we enter this ELM-free regime, which is the hallmark of this NT ELM-free scenario that we've been very excited to look at. And so this is potentially the first negative triangularity data on spherical tokamaks, which is expanding the regime to a different aspect ratio, which will be very fun to look at in future experiments. On the whole, MAST-U and D3D comprise just part of a big global data set, a growing global data set of NT data. You'll see talks today about TCV as well as ASDEX, and I think there's also a JET talk coming very soon, right after this, which is not plotted on this plot. But this is good news for negative triangularity, which has gone from very little data about a decade ago to lots of data on various machines in the present time, which is rapidly expanding our ability to create engineering and non-dimensional scaling laws and adding high-value discharges that can help us learn how this regime behaves under different scenarios. So with that, I would like to conclude, but I'd like to point out first that there has been a lot of recent progress in negative triangularity scenarios, much more than I could cover in 15 minutes. If you'd like to learn more about it, there is a large collection of negative triangularity in the physics basis, which is the webinar that we're talking about today, but also a dedicated website just for negative triangularity papers related to D3D work, which can be found here or at the QR link shown as well. So yeah, thank you for your attention, and I think we have 5 minutes for questions now, so I welcome anything you have. Thank you.
Thanks a lot, Oak, for the, I think, very, very nice summary of a lot of work between D3D and MAST as well. So one question is on the statement you made quite early on about the n=1 stability. And so maybe could you comment on, first of all, what is the concern about the n=1 stability and the reason for why you don't think it's a big issue?
Sure. So one of the things, as I mentioned earlier as well, negative triangularity is predicted and seen to have worse MHC stability in general. And so this happens both in the edge. I talked about the ballooning mode as an example of this, which is limiting your pedestal gradient. It turns out that a modern look on this actually considers the ballooning mode, for example, to be a good thing. Even though it's poor MHC stability, which is limiting your gradients, it's preventing you from going to these ELMing regimes, which is something that we can't have in a reactor. The n=1 stability in particular refers to things like the beta n limit, which is also slightly reduced for negative triangularity compared to positive triangularity. On D3D plasmas, there are several studies by William Boyce that look at the MHD in experiment and extrapolate this to reactors. And what we've seen on D3D is that we're able to get up to reactor relevant levels of beta n, even with potentially reduced ideal limits, etc. And so even though there is a reduced ideal limit compared to positive triangularity experiments, it's not so reduced that the regime becomes irrelevant. It's still very much a relevant plasma for reactor scenarios.
May I make a comment on that? It's quite well known that ideal MHD is sensitive to interchange terms or Mercier type terms, and these have to do with the average curvature of the torus, and in fact all the kind of ideal instabilities are made more unstable by negative triangularity. Of course, that's the whole point of the ELMs. You want to reduce the stability boundary, but it could also have an impact on tearing modes as well, because the tearing modes tend to be a little bit more unstable as well. You even saw those plot just now.
Yeah, so in the D3D data set, we have looked at tearing modes, and we don't see a significant difference between tearing modes and positive triangularity and negative triangularity. And so at least from the D3D data set, this also looks to be more of a worry than it is an actual thing that's playing out in practice.
The second question is on the MAST results. Have you done any analysis on what sort of turbulent regime the MAST that particular MAST discharge is in?
We are just starting the turbulence and confinement analysis for these plasmas actually, and we hope to scan a bunch of the parameters. So I think it's still too early to give any real conclusions about turbulence and MAST.
Okay, and maybe one final question. Are there plans for future negative triangularity experiments on MAST upgrade?
Yes, there are. We should have a series of experiments coming this fall and winter. One of the goals of which is to study turbulent transport. So check back in 6 months and we should have some good answers there.
Excellent. Thanks a lot, Oak.
My pleasure.
So moving on, the next speaker we have is Olivier Sauter. Olivier is a senior scientist at Swiss Plasma Center at EPFL. I also feel confident in saying that out of all the speakers today, Olivier has been working on negative triangularity for the longest, really way back, starting at the very earliest experiments on TCV. So thanks for being here, Olivier, and start when you're ready.
Thank you. I hope you can see my slides well. So today I'm speaking about the JET experiments, since you will have some results from TCV later on. And it's a bit a special experiment because everything happened in a bit less of a one-day experiment. So the time constraints were also quite exciting to see what we could do within such a small amount of time in the biggest machine that we had to test negative triangularity and the biggest machine at that time. And I will convince you that we did reach quite a nice set of results. Why do we wanted to do the negative triangularity on JET? Mainly, of course, because it's the largest tokamak, and that's therefore a key data point towards NTFPP. One of the main questions for prediction for a demo reactor is if we can certify that we will not have any ELM or disturbances from the edge when we have really high power flowing through the separatrix. So that was one of the main aim, of course, of this study. And it was also to test with different kind of walls than we have in D3D and NTCV, where we have most of the data so far. And you see here the range of triangularity that we reach on TCV or in D3D, a large range. We have more limited access in the other tokamaks, but still each of them bring a new set of data and very important results to have the whole story for predictive capabilities. So the first question is, of course, was also, is it worth a try? And so when we received the first predicted equilibria from Peter Lomas, this is the kind of drawing and separatrix boundary I received. And then I did what Oak mentioned. We computed the access to second stability of the ballooning modes, and to see if it was closed or at least marginally closed. And indeed, with such a top delta, so sorry, I forgot to mention, on JET, we could not have both negative triangularity on top at the bottom. So we kept the X point as usual for the JET plasma, and only the top triangularity was moved to negative values. And we could foresee to reach values around -0.3, which is just below the delta crit that Oak mentioned. So it was worth the try, which we did. And here, just a few shots. We started with the shot number 105.822, which was just a test to see if everything was working right. The 23 was the ohmic test of the shape to make sure that we don't touch the top wall. Then we tried with 10 megawatts with the 24 here that you see in green. And you see that already with number 33, we could go up to 32 megawatts in total on a machine where we, even though it was the last day of experiments, nevertheless, we didn't want to break it. And so we were careful. But what remained true is that we did not have any ends. You can see here from the beryllium. Sorry, I forgot to change the y-axis from the beryllium emission. We can see that there's no perturbation even up to 32 megawatt. This is the dashed line, is when we reach 32 megawatt. You see no changes as compared. Here I just put a similar current and magnetic field, so 1.4 megaamp, 2.2 Tesla in positive triangularity LMH mode versus 1.5 megaamp, 2.3 Tesla in NT. You see that indeed we don't have any perturbation, and because we don't have this perturbation, we can see a natural continuous evolution. When we increase the power, you can see the power increase, the beta increase, and we can control very well the plasma actually. And so we could, with confidence, go quickly to the full power that we had available at that time. If we look at a bit more in detail the comparison for these two discharges at 12 and 32 megawatt, you can see that there is no perturbation on the tide temperature either. So this confirms that there is no ELMs. We go to high stored energy. We have beta n around 1.6 for the highest power. Green wall fraction around 0.8 in a stationary state. The H factor we will discuss later. Actually, for this first high power, I put much more gas in, and you see here the gas flux was around 60 as compared to 15 in the first. So I wanted to make sure that everything was fine. So of course, this does not help for confinement. This is known also for positive triangularity. But we know how to improve, but of course we didn't have time to improve on that day. But nevertheless, the results, which was the first result, was to check that indeed we can have no ELMs up to 32 megawatt, which is of course the largest. This is the world record no ELM power through the separatrix. And then if we look at the profiles, you see that they are very similar to what we just saw from D3D, and we have the same, you will see later on TCV. You have slightly larger gradient for the density and a mild gradient for the temperature, with essentially a pedestal which is around 0.708 for the pedestal, and this reflects on the pressure, sorry, which is what we saw from Oak's diagram as well. So all this is consistent. So in this sense, we can see that we don't have a significant size effect. To test this further, now we can use the jet shape into TCV, for example, and hopefully other tokamaks, to compare with the size effect with similar shape. So we reproduce the jet shape. We don't have exactly the same aspect ratio, so then we have to change slightly the aspect ratio, but otherwise the top and bottom delta we did reproduce and slightly lower elongation, in fact. And we could also confirm that we did not go into ELMI regime, even if we are 2 times above the L2H threshold, all in forward Rod B direction. If we look at the time evolution, here we did a power ramp in TCV. You see that the beta just keeps going up. The H factor actually is going up because in this type of parameters, the confinement is less degraded with increasing power, so we benefit from the H scaling. This is a discussion we will have to have across tokamaks to have a better scaling with negative triangularity, of course, so that we are not biased by our analysis. So this is work ongoing, but nevertheless, this shows that if we go, with the H factor and then the green fraction and the beta n as we saw on D3D, and we will see later on JET, we can have very nice analysis. And of course, what we can further do on TCV is to change slightly the top delta, for example, more negative, and to go to higher power. We reach maximum input power, which on TCV we reach beta n of 2, still remaining. You see the continuous increase of beta with power and remaining in no ELMe case. Now, if we go back to the jet experiments, so once we had tested the H mode, not the ELM access, so no ELM access in some sense up to the maximum power, we wanted to test other operation limits, for example, the Greenwald fraction. So we had actually two pulses because the first one we didn't puff enough to reach the density limit since it was quite high. So at the end, we reach above Greenwald fraction of 1. It's not quite a density limit disruption, but at least we saw we could go above 1, and that's what we wanted to prove. We didn't have time to further study this part, and also at very high density, it's hard to keep the NBI power on, so that's also degrading the density limit as mentioned earlier by Oak. Nevertheless, this proves that we don't have a worry about the density limit even in a jet type plasma. We also did one pulse with the magnetic field ramp. We went down from 2.5 to 1.45 Tesla. That's what we could ramp down. It was not quite sufficient to reach the limit, so we did not disrupt because of the beta limit. So we know that at least in this type of plasma, the ideal limit is above 2.8. That's what we reach about. And we also, at the same time, of course, you change Q95, we kept plasma current constant. And so we reached Q9503 without any problem. We didn't have either any NTMs in this whole days coming up. So there's indeed not a significant difference with positive triangularity on that respect. We know from TCV and D3D that it's easy to go below Q9503, which is also good because Q95 is naturally lower in negative triangularity than in positive. So since plasma current is the main driver for confinement properties, good confinement properties, that's what you want to use. And you can see that in these cases, the H factor starts to be up to 0.8-ish. In the phase where we have clearly no ELM, we start to have some limit cycle at the very end. But you see that we span, if you want, the H factor from 0.6 to 0.8, which is consistent with the fact that our negative triangularity is just below the delta crit. So that's when we start to have the improved confinement kicking in. And of course, if you would aim for a reactor, you would want a more negative top triangularity to benefit from the improved confinement. If we look at the profiles, so the first one, this is the B ramp. So this is at the time when we are at beta n of 2.5, green refraction is around 0.7 and 23 megawatts, no ELM. This is this is the red traces. So again, you see the density at the top of pedestal is around 0.9, not 0.95 or more like in H mode, nevertheless. And for the temperature, it's around 0.8, 0.7, 0.8. And for the density ramp, when we are near Greenwald fraction of 1, we stayed at about 14 megawatt, maybe slightly less actually. So the pressure is a bit lower, but you see that the profiles are very similar. There's no sign of sharp pedestal at the edge, and rather the top of pedestal around 0.8. And this is really what is the main driver for the good sign of the good effects of negative triangularity, is that since we don't need to have a power above a given threshold, like when we go to H mode or the no ELMe H mode, but in positive triangularity, then that's much easier to sustain the plasma, to control it. We did not see excessive radiated power despite the beryllium and tungsten wall and diverter. And so this was easy to control and to go through the experiment. Here we do a comparison with the QC, which was also developed as an OLM regime for JET, starting from ASDEX and then TCV. And now within WP, the Eurofusion program, we go to JET. This was also developed for DT QC. We had more experiments, but if you compare, I will come mainly to the profiles. We have similar beta N, similar confinement, a bit less lower confinement, a bit lower beta N for the NT, but also because we did not have time to optimize the discharge. Nevertheless, if you look at the profiles, you see now really the difference between a true H mode-like pedestal in the positive triangularity QCE case, especially on the density. On the temperature, you have to zoom, and you would have to look at the gradient, the maximum gradient. It's still around a factor 2 difference if you look at the details. But you see here, if I put an arrow between looking at kind of the top of pedestal, you would be at 0.95 here. At this value, at the similar value, you are about 0.8-ish. So you have about 3 or 4 wider pedestal width, which means 3 or 4 lower gradients. And that means an alpha value, which is 3 to 4 times lower. And indeed, just kind of to wrap up with the previous talk, because we closed the access to second stability region with the negative triangularity, we are clamped to alpha values around this corner. If we compute on a given one of the cases a jet, this is the diagram we get, S versus alpha. If we have a strong edge current, we could lower the shear enough to go to higher values, but in our case, we were just marginal for that. So we stay around alpha values of 1-ish or 1.5, 1.8-ish. Whereas if we would go to, like in QC, to have access to second stability, then alpha directly goes up to 3 or 4. That's the difference showed you jump to 3 or 4. And therefore, you see this factor 3 or 4 that we saw on the pedestal. Now, just an overview on the confinement database. This is using the pedestal database from Lorenzo Frassinetti. Here, Benoît Labit plotted over the values of the H factor and the Greenwald fraction that we had in this set of shots. We have a total about 15 shots here, but 10 are plotted. And you see that we are really nearby, but it's understandable from the lowish triangularity. But nevertheless, we can compare with the H mode pedestal database, which means that even at the size of jets, we can compare an NT-L mode type edge with an H mode positive triangularity type edge. So I can come to my conclusion. So that was the last day of jet experiment. So that was quite a nice adventure, actually. We could do about 15 good pulses we had less than 1 day available for us. And nevertheless, we reached 32 megawatt, 1.7 megaamp. I didn't have time to show at 2.3 Tesla. We had stable operation with no ELMs at this level. We had two pulses at 32 megawatt. I showed you only one. The other one with less gas or a bit better confinement. We did one ramp down, so we showed we could reach high beta N, about 2.8, and Q9503 without disruption. We could test the density limit, at least one pulse we managed to go above the Greenwald fraction. The other one we didn't have enough gas flux. We have confinement properties up to 0.8 in our cases with the shape we had. And so, of course, these are preliminary results. We have to study more and to look at the local transport and other quantities. But we also have this ability to compare with TCV, ASDEX, D3D, and MASS, of course, and SMART. But if you look at the TCV to jet prediction, it's actually maybe even less than the jet to FPP type prediction. So I think we are in a good place to make good predictions for reactor like tokamaks. Thank you.
Thanks, Olivier. Nice talk. So there's a number of questions, one on scaling, in particular with heating power. So the question is power degradation for negative triangularity similar to power degradation in H mode, or is it worse?
No, I think I cannot answer just in one word, because I don't think the power degradation is just similar to positive triangularity H mode. I think we have very small degradation at lowish power, so we can really profit with increasing power, increasing the pedestal pressure, and I think it corresponds. We have to demonstrate this, but this corresponds to going from lowish pressure gradient at the edge towards the first ballooning limit, and then we kind of saturate at very high power. And so then you would say, the power degradation is very strong. So it depends where you look. But of course, when you do a prediction for a reactor, you will choose. The nice point is that you can choose a point which is not at too high power, where you benefit from confinement, but you don't need to put a lot of power because you don't need to be above the LH threshold. Sorry.
Okay. Another question on the H factor and it being rather low. Do you have any more comments on that? And then kind of a related question is, in the first point of your conclusions, you said that, this was all done in one day. And so, in your experience on TCV and D3D and other machines, is there, if you had more time, do you think that the H factor could be improved?
Yeah, so as shown, we have a paper actually we did on TCV. The confinement improvement does go with the negative delta. So the more negative, the better the confinement, especially the more negative the non-X point delta, as Alessandro will show probably. And in our case, we know that when we are with a negative delta just sufficient to avoid the ELMs, then that's the beginning of the improvement that we can measure, if you want, with our standard diagnostics. And so we knew we would be at the beginning of this part. So I think it's normal that we were at the lower end from what we can expect. So if we had the possibility to go to minus 0.45, minus 0.4 for the top delta, then I think we would be above 1 for the H factor. But we need a DTT to prove that, I guess, for the next talk.
And one last clarifying question on, you mentioned that there are similar profiles between JET and D3D and TCV. By similar, do you mean like the peaking factor, or you mean the shape of the?
We mean also the shape. We have an experiment going on ROSTA scaling and similarity experiments with dimensionless parameters between D3D and TCV. This is led by Alessandro Marinoni, and there we can see better what it means in terms of dimensionless parameters. So look forward for the next paper.
Okay, thank you very much, Olivier. Our next speaker is Tim Happel. So Tim is the head of the Plasma Physics Division at IPP Max Planck Institute near Munich. So he studied negative triangularity, obviously, but also the improved confinement regime I mode, and actually did his PhD developing turbulence diagnostics. So Tim, whenever you're ready, go ahead and begin.
Okay, thanks, Justin. I just assume that you're hearing me and that everything's working fine. So first of all, I'd like to thank very much IOP and PPCF for giving me the chance to present this work. I'm sorry, my camera just came up here. Give me a second. Okay, for presenting this. And so this is work on negative triangularity on Astex upgrade. And I'd like to point out that there are major contributions in these slides from Branka Farnafats and from Lorenzo Ocone, and that the whole Astex upgrade team has contributed a lot to this work. Also, not only that, there have been collaborations going on with many institutes institutes worldwide, and also in Europe within the Eurofusion umbrella, which has which we've benefited quite a lot. Now, in the PPCF special issue, we have these 4 tokamaks, so to say. We have the 3D, TCV, ASTIX upgrade, and MANTA, which is a design of a negative triangularity reactor. And this talk only focuses on ASTIX upgrade. And you see here already, this is our most negative triangularity shape. And if we go into the vessel of ASTIX upgrade, it looks like this. So this, just to give an overview, this has a major radius of 1.65 meters and a minor plasma radius of 0.5 meters. So actually a person can stand in here. And we have various auxiliary heating methods. And I will come back to this at the very end of the talk. The average delta we can obtain is minus 0.2, and this is comprised of an upper delta of minus 0.4 roughly and a lower delta of 0. So actually our negative triangularity is somewhat limited. Still, the studies are important for the physics understanding of negative triangularity and also for DTT. Now, if we step out of the vessel again, this is our configuration. So you see that the inner wall of ASTIX upgrade is very much adapted to the plasma shape we usually run, a positive triangularity. So it's kind of hard to run a negative lower triangularity, just like in JET, what Olivier has shown before. But also our shaping coils are all not only outside the vessel, but also outside the TF coils. So these purple ones or magenta ones here are our shaping coils. So our shaping capabilities in that sense are somewhat limited. But if you look at the design of DTT, you see here the shaping coils are also outside of the TF coils. And so what we did in the last campaign, we ran anti-equilibria that were similar to the ones DTT will be able to run. So the results from ASTIX upgrade could be relevant for DTT. Now, if we take this plasma now and we make it negative triangular, then we see this is our most pronounced NT shape, where we have an upper triangularity of minus 0.45 and the lower one is roughly 0. On the right here, you see a radial profile of the triangularity. So you see here the upper triangularity, which is very negative in the very plasma edge, where we have this ear. And then if you go towards the inside, it maintains a negative value, while the lower triangularity is positive throughout. And one might wonder why this is the case, why in the center we still have triangularities, even though the plasma surfaces, they look rather round. So this is because these are ellipses, which are tilted with respect to the vertical axis. And this is why we have, so to say, an apparent negative triangularity here. But if you start at 0.7 towards the edge, then this is a real negative triangularity effect here. So in terms of peeling ballooning stability, this should actually yield a significantly reduced pedestal performance, and this is of course something which we would like to have. Now, if we take such an equilibrium, a little bit different from that, and we run a negative triangularity, then here this looks complicated, but it's actually pretty simple. We have ECRH power steps here, and this is 1.5 megawatts. This is roughly the typical LH transition threshold power. So here at the end with 4.5 megawatts, we are at roughly 3 times the LH transition threshold power. And what you see is that the electron temperature goes up together with the heating steps. The ion temperature stays roughly constant, but the plasma energy goes up here. And you also see the confinement improvement factor going up and then saturating. And this is reminiscent of what Olivier just said. So at lower heating powers, we're still gaining confinement, so to say, while at the end here, when we are at roughly an H98 of 1, we do have H-mod-like power degradation. And this is also consistent with results from D3D. Now, I've marked here time windows at the bottom of the plot, and I'd like to show you some radial electric field profiles in these time windows. And what you see is that at the lowest heating power, the black profile, you have a very shallow radial electric field. This is minus 4 kilowatts per meter. Typically in H-mod, we have minus 15 kilowatts per meter. And then when we increase the heating power, the minimum of the radial electric field increases actually. So this is clearly an L-mod plasma. We do not have any ELMs, and we do have good confinement here. But this is not always the case. Here's another case where we add heating to the plasma discharge. And then you see here, these are diode bolometers. You see at 3 seconds we enter H mode, and we have irregular ELMs in the beginning, and then they become more and more frequent, and the ELM frequency goes up to about 700 Hertz, which is actually comparable to results from TCV and also D3D. And here the question is the delta not negative enough, or is the shaping not enough? Yeah, so there has been work on this, and for to avoid the access to the second stability region. And I think in the end I come back to that, and I think we should work on this and try to make this robustly stay in L mode. Now also here, like in the previous plot, I show you the radioelectric field profiles for these time windows marked at the bottom. And you see that when we're in L mode, the radioelectric field is rather shallow. And then once we are here in H mode, we have really significant ER wells with values of up to minus 30 kilowatts per meter. So these are clearly H mode plasmas. Now, in the context of the special issue, Branka Vanovat she took these radioelectric field profiles in different discharges. And what you see here is here's one profile which stays in L mode, these dark red points, and then here in blue you have another negative delta discharge with a strong negative ER, and this is in H mode. And here you see also a strong negative ER. We only have 1 point because the diagnostic was not working so well, but it gives you an indication of how deep the ER is there. And on the right hand, in the right-hand plot, we look at the radiation temperature fluctuations, which are measured with correlation electron cyclotron emission. And we see that for this flat profile here, we have high fluctuation levels, and for the H mode cases with strong radioelectric field minima, we see that the fluctuation levels are actually lower. But also this low ER discharge here is close to the infinite and ballooning limit, and this actually asks the question, what is the gradient limiting mechanism here? Oak touched on this in his talk quickly when he talked about the distance to the infinite and ballooning limit, and that there's a large scatter, and maybe the turbulence might play a role here when you have very large fluctuations, that the gradient actually doesn't go up to the limit. So this could be maybe an idea. Maybe we can talk about this in a panel discussion. We also looked into the performance of these discharges, and in this context, Lorenzo Arcone looked at electron pressure profiles, which are shown here. And what he has done is he has compared negative delta with positive delta for low and higher heating powers. And you have the solid lines, which are experimental values, and then you have the dashed lines, which are predictions from TGLF with the SAT2 saturation rule. And you see that the predictions from TGLF are pretty good. What you also see if you focus on the very edge is that in positive triangularity, these are H modes. You have this pedestal here, while in negative triangularity, you don't have the pedestal. But what has already been said before, the gradient catches up at some point, in this case here at rho toroidal 0.5, and here a little bit earlier in this discharge. And this loss at the very edge can be recovered. And inside of rho toroidal 0.5, the profiles are rather similar. Now, Lorenzo looked into the performance of this. So he took the average pressure inside 0.5, and there we see that the negative triangularity can be as good as positive triangularity H mode. But if one looks at global parameters such as beta n here, for example, then it's a bit weaker because we actually lose this pedestal contribution to these global quantities. And in the pedestal or in the very edge, the plasma volume is very large, so there is some significant contribution from there. What Lorenzo has done here is this is the prediction from TGLF for the ion pressure, which is actually important for the fusion power. And in this case here, the NT prediction is very good, but here it stays below the positive triangularity prediction. And so the ion channel is still something I think we need to investigate. It shows strong transport here, and there I think are more studies are needed. For example, Alberto Mariani has done this in a recent paper. So this was on the performance. And what Lorenzo also did in his paper, he looked a little bit into ELMs, and he has a very simple yet striking plot. This is shown here. So this is at the radius 0.9 and the temperature. And you see for negative triangularity, you just have this very small fluctuations, while for positive triangularity, you have the effect from the ELMs. Yeah? So in negative triangularities, this is much more benign. And Branka looked into this in more detail. And you see here in dark purple, the relative energy loss from the ELMs when we run into H modes in negative triangularity. And this is below 1% relative energy loss. And if you compare this to type 1 ELMs, which are 4 to 10% or even higher, then this is clearly much more benign. Branka also scanned the average triangularity. And when we go from positive to negative triangularity, the ELM frequency increases. And this is very reminiscent of studies done 12 years ago on TCV, where Brachelon scanned from positive to negative triangularity. While he did this, the ELM frequency went up and the relative energy loss decreased in this case. So we looked into these ELMs, but actually it would be good if we were able to avoid them. And for this, we've been in touch with Oak, and I'm thankful that he has already introduced this kind of plot. So here you see Aztec's upgrade, the vessel, and you see some equilibria which Oak has calculated. And if you focus on the blue one, which is something we cannot run because it intersects the vessel here, then the access to the second stability region is closed. Yeah, we would be sitting down here. Now, if we go to the black one, then it's still closed, but once we start with the yellow and orange ones, then we can access the second stability region. So there might be a way on Aztec's upgrade to look for a shape that just avoids accessing the second stability region and making our NT edges more ELMed and more solid without ELMs. This can actually also be done with the upper triangularity. If we manage to change this a little more, then we might be really in a state where we don't access the second stability region. So this is what we've done. The NT studies in Aztec's upgrade are challenging, but they are relevant for physics understanding and also I think for DTT. We see significant differences in the edge radial electric field and turbulence between L mode and H mode. And the performance of the core electron pressure, at least, can compete with positive triangularity H modes. The ion pressure so far is a bit unclear. And the ELMs in H mode NT plasmas are fast and they cause relatively small energy losses. Now, I'd also like to say a little bit about future studies. So we would like to go on with H mode inhibition via the shape. And we would also like to look into the behavior with different dominant turbulence mechanisms and switch between TEM and ITG. And this is what we can use our different heating methods for. So we can use neutral beam injection with reduced voltage, then we can heat the ions at low density and try to switch on ITG and switch on TEM with the ECRH. So this is something we will try. And also look into the effect of neutral penetration on the performance, which is again under the Eurofusion umbrella. What I think is important to do is to do theory and numerical investigations, and I've underlined this here, comparisons with experiments. I think we should try to use full F codes such as XGC or GNX to investigate the edge and pedestal transport and look at the influence of the scrape-off layer on the separatrix values. And we should also do gyrokinetic and nonlinear simulations in this region where we have the strong gradients to understand the behavior better there. And then the final question is, of course, how do these properties scale towards larger machines or other aspect ratios? And here, of course, I'm happy that the next talks will focus some points on that. Okay, that's it. Thank you very much for listening.
Thanks, Tim. So one question is, why is it important to avoid the small high frequency ELMs?
That's a good question. So in principle, you could, of course, argue that when they have such a high frequency and such a low relative energy loss, that they might not be so critical anymore. That's even the concept of the QCE, of course. But it might, of course, be that some of this doesn't scale to a large reactor. So if you manage to avoid them altogether, I think it would be, you would sleep better. at night.
Okay, and a clarifying question: the shots by Akone, Lorenzo, did they recover the on-axis values of pressure of an H mode, and did they also not have ELMs?
So these ones, so this is a bit involved. This negative triangularity plasma here has an NT edge, so this is without ELMs. The one down here is a negative triangularity plasma, which did enter H mode, and this one does have ELMs, but as I said, these high frequent ELMs.
Okay, thanks. John? You're muted.
Thank you. I was going to make a comment on the small ELMs. I think we know the EU demo won't be able to handle any ELMs at all. But I think there are some that say even ITER won't be able to take small ELMs as well. So the ELM-free, fully ELM-free scenarios are going to be important. But I wanted to just look at some of the profiles that you were showing earlier, where you showed the pressure profiles, but it seemed like in the very core, in the region 0 to 0.2, 0.23, there was a significant flattening of the pressure near the axes. And is that related to the previous question that Oak had on the core instabilities like sawteeth and so on, and their effect perhaps on flattening the pressure in the very core?
This flattening here is due to sawteeth, yes. So yeah. Lorenzo incorporated a model here for sawteeth, and he included that. Yeah.
So we're seeing very, very frequent, very small sawteeth as well in these experiments.
I would have to have a look at the discharges indeed.
But anyway, I was going to make the comment that that could be very good for destabilizing tearing modes as well. I mean, we don't want tearing modes to be triggered by sawteeth, so that's another advantage in small grassy sawteeth that's that you seem to be showing there in your plots.
Okay, thanks, Tim.
Thank you.
So next up, we have Alessandro Bellestri. Alessandro is a PhD student, at the Swiss Plasma Center at EPFL. I think so far his entire career in fusion research has been on negative triangularity in his master's and now his PhD, and he's aiming to bridge the divide between theory and experiment, which we'll hear about today. Go ahead.
Okay, thanks, Justin, for the introduction. So my talk will be on how we can explore the effect of negative triangularity on turbulent transport with experiments on the TCV tokamak and gyrokinetic simulations. So we already saw very nice presentations on negative triangularity, and so the advantages that we can have. So robustly inhibit access to H mode, and so we have an intrinsic ELM-free scenario. But then we can still recover H mode-like performance by reducing turbulent transport. And so in this talk, I will focus on when and why we observe this reduction of turbulence. And so the presentation will be divided in two parts. In the first part, I'll show you exhaustive experimental evidences of H mode-like confinement of NT plasmas on TCV. And so I will focus on the confinement properties analysis of the negative triangularity TCV database, and then also more in depth showing the results of an experimental experiments on the TCV tokamak for DTT operations. And then I will focus more on the results from gyrokinetic simulations, trying to explain the beneficial effect of NT on transport. And I will focus on electrostatic turbulence and how the aspect ratio can change the beneficial effect of NT, and then same thing on electromagnetic turbulence. So moving to the experimental part, let me say that, yes, the revival of NT plasma started indeed at TCV with the very famous paper from 1997. And since then, actually around 5,000 discharges with negative triangularity have been produced on TCV. So it's quite large data set that it's worth to analyze. And so, of course, we downsampled a bit, choosing, according to some parameters, 631 ELM-free negative triangularity shots. And this plot here is complementary to what Oak showed before. So on the y-axis, we have the H factor, on the x-axis, beta n, and the colors are different values of Q95. And indeed, we also in TCV, we observe that when beta is sufficiently large, in this case, when beta is larger than 0.6, we can achieve H-mode-like confinement, and also lowering Q95. So when Q95 is lower than 3, this is even more, this is easier. But then let me show you with this DTT-NT similarity shape how we can achieve actually H-mode-like confinement. So as team showed us for ASDEX upgrade, we also reproduced the NT and PT shapes envisioned for the DTT tokamak on TCV. And we heated these scenarios with 3 different heating mixes. And we, for these heating mixes, we always had 3 scenarios. So a negative triangularity L mode, a positive triangularity L mode, and a positive triangularity H mode. And the 2 L modes were produced with the same heating power, and the H mode instead with double the power. So then, yeah, I will focus on the NBI part, but actually we have the same results with the other heating mixes. So if we look at the kinetic profiles, and so here I'm showing the electron density, here the ion temperature and the electron temperature as a function of rotor. And in black we have PT L mode, in blue we have negative triangularity, and red is positive triangularity H mode. So if we compare blue and black, so NT versus PT L mode, we see that basically we achieve larger temperature and density across the whole plasma radius. So we have indeed better performance. But then the interesting comparison is between NT and PTH mode, because we can reach the same or similar density and temperature of the H mode. And I just want to stress out that the H mode was produced with double the power. So we have H mode-like performance in the core with half the power in negative triangularity. But then you may wonder what is the origin of this improvement. And so this is this plot here is consistent with the 3D results and also jet results and also ASDEX upgrade. And so here I'm showing the electron pressure as the function of rotor across the separatrix. And indeed, if you compare again NT versus PT in L mode, which is the one in black, you see that we have larger values of pressure at the separatrix and also in the very edge. And this is due to steeper profiles in the scrape-off layer. And let me say this is consistent with other experimental and theoretical works. But then there's another important effect, and this is due to increased logarithmic gradients, again, with respect to positive triangularity L mode. So here I'm showing the electron temperature logarithmic gradient, the electron density logarithmic gradient, and the ion temperature logarithmic gradient, again, as a function of rotor. And here, if you compare blue with black, you see that indeed in NT we have larger gradients, basically between 0.8 and 1. And so this is always a symptom or synonym of better transport, or if you prefer, lower transport in negative triangularity. And indeed, we confirm this with gyrokinetic simulations, showing that indeed we have a stabilization of TM-driven turbulence. But then, so since turbulence is key, let me move to the second part of the talk. And so I want to highlight again that to recover H-mode-like performance, the beneficial effect of NT on transport is fundamental. However, we still miss a complete understanding of this beneficial effect and how it can change depending on the turbulent regime. And so here I will focus on 3 regimes, so or 3 types of turbulence, so ITG, TM, or MTM. And also we study the influence of other geometric parameters on NT. And in this talk, we will focus on the influence of aspect ratio, so the ratio of the major radius over the minor radius. So let's start with the electrostatic part, so ITG and TM turbulence. And I will start filling this plot here with results from flux tube nonlinear gradient-driven gene simulations, where we changed the aspect ratio artificially, starting from reference TCV and D3D scenarios. And so on the x-axis, we have the aspect ratio, and on the y-axis, we have the ratio of the heat flux in the negative triangularity geometry over the heat flux in the positive triangularity counterpart. And so when this ratio is below 1, NT has better confinement, and when the ratio is above 1, NT has worse confinement than PT. So if we consider the ITG regimes, and so we have 2 pure ITG regimes from a TCV scenario and a D3D ITG dominated realistic scenario, we see that NT has always better confinement than PT at any aspect ratio, from large to small aspect ratio, so also in a regime typical for a spherical tokamak. But then if we consider a TM scenario, and actually here we have a TCV TM dominated scenario and also a TCV pure density driven TM scenario, we see a different picture, because at large and conventional aspect ratio, we see the beneficial effect of negative triangularity. But as we move to small aspect ratio values, we see that now we lose the effect of the beneficial effect of negative triangularity, and now we have worse confinement than in PT. So we can identify two regions. The first one here in the red shaded area, where we have conventional and large aspect ratio tokamaks. And here, as I said before, we see that indeed we have better confinement in ITG and TM in a negative triangularity geometry. And also let me say that this is consistent with many other works, both theoretical, numerical, and experimental. So I think that we have a quite consistent picture that indeed NT can stabilize quite efficiently ITGs and TM. Instead, in spherical tokamaks, we have the different picture. So we can have the beneficial effect of NT only in ITG, but let me specify that these are simulations, and so it would be great to have experiments both on MASTU and SMART. So with this, we can start filling this scheme here. You will see it also close to the end. And so we can color with green these two boxes for large and conventional aspect ratio tokamaks, and instead we can color in green only the ITG box for small aspect ratio tokamaks. And we think we understand or have a simple physical picture of why NT stabilizes ITG turbulence at large and conventional aspect ratios. And this is due to stronger FLR effects around the outboard midplane and also faster magnetic drift around the outboard midplane. Unfortunately, for spherical tokamaks, the picture is still unclear. So there's a strong nonlinear interaction between many different factors, and so we're still working on this. But so with this, let me move to the second part. So on electromagnetic instability. So you may wonder why bother with electromagnetic instabilities. Well, because in fusion plasmas, we should reach large values of beta, and when beta is sufficiently large, we can trigger electromagnetic instabilities like the microtrim modes, MTMs, or kinetic ballooning modes. But here I will focus only on MTMs. And so we considered many different scenarios, as you can see here in the picture. So D3D, SMART, Demo, TCV, MASTU. So very different machines characterized by different aspect ratios and also size. And we perform gene local linear gradient-driven simulations, always flipping the triangularity. And let me say that these we cannot, for now, rely on non-linear simulations because either they are too expensive or they do not converge. So for now, they are still not reliable, and we have to rely only on linear simulations. Before I show you the results, let me give you a very simple physical picture of the MTMs. So for these kind of modes, the parity of the vector potential allows for field line breaking, which then allows for deformation of small-scale magnetic islands, which then increases the magnetic stochasticity, which then, of course, leads to unconfined electrons, and so radial transport. And these three boxes are related to specific parameters, like the magnetic shear is related to the size of the islands, the stochasticity is related to finite values of beta, and the transport of electrons is related to gradients in the electron temperature. So we scanned these three parameters with linear simulations to see how the MTMs were changing in NT versus PT. So I will show you a lot of these plots. So let me guide you through the parameters. So on the y-axis, we have beta in percent. On the x-axis, the ratio of the electron temperature gradient over the ion temperature gradient. And the colors are the real frequencies of the modes. And so what you have to remember is that when you see red, we have ITGs. When you see light blue, we have TM modes. And when you see dark blue, we have MTMs. So with this in mind, we can see we can look at the overall picture. Here we have all the machines. So first column is TCV, the second one is D3D, then Demo, then SMART, and MASTU. And going from top to bottom, we're increasing the magnetic shear. And these are simulations for scenarios with negative triangularity. And here we see a consistent pattern because all these scenarios can enter a regime where MTMs are dominating, and this can be achieved when beta is sufficiently large, the magnetic shear is sufficiently large, and the ratio of the gradients is larger than 1. But then the interesting thing is that if we flip the triangularity, so if we go from NT to PT, as you can see here, all the blue windows disappear, or almost all the blue windows disappear, meaning that in positive triangularity scenarios for the parameters that we considered, we only have ITG modes. And so this is already telling us that somehow MTMs are more unstable in NT, meaning that they are or subdominant or completely stabilized. But we can look at this comparing the growth rates of these modes. So again, same axis, so y-axis is beta, x-axis is the ratio of the gradients, but now the colors are for the difference between the growth rate in PT minus the growth rate in NT, normalized for the growth rate in positive triangularity geometry. And again, what you have to remember is that when you see red, NT is more stable than positive triangularity. When you see blue, NT is more unstable than PT. And so again, looking at the overall picture, we see two interesting features. The first one is that, again, when you see red, NT is more stable, and this is where ITGs are dominating in negative triangularity. And this is also consistent with the first simulations that I showed you. But then when you see blue, again, this is where NT is more unstable, and this is where MTMs are dominating in negative triangularity. So indeed, they are more unstable in NT than in PT. But then let me stress out that this is not necessarily an issue for conventional tokamaks, because if we plot the reference parameters of our scenarios, so the stars here on the plots, you see that TCV, D3D, and demo can live outside the blue region, and so outside of the region where MTMs are dominating. Instead, the spherical tokamaks could live potentially in the blue region. And so because in spherical tokamaks, because of their nature, we can achieve already at the edge large values of beta. And so we can fill again the scheme, and we have to put a red color for both large and conventional aspect ratio tokamaks and spherical tokamaks for the MTMs. And also for MTMs, we have a simple explanation of why they are destabilized in negative triangularity, and this is due to faster averaged magnetic drift. And with this, let me move to the conclusions. So we saw on TCV that we can achieve M3 H-mode-like confinement, especially when beta is sufficiently large. And with the DTT similarity shape experiment, we observed that the negative triangularity option can achieve H-mode-like performance without ELMs, at least on TCV, and less heating power than the H-mode counterpart. And then from the simulations, we saw that NT can stabilize ITG turbulence both at conventional aspect ratio and small aspect ratio, so in spherical tokamaks, can stabilize TM turbulence only in conventional tokamaks, in conventional aspect ratio tokamaks, and finally, it is destabilizing for MTMs both at conventional aspect ratio and small aspect ratio. And with this, I conclude. Thanks.
Thank you, Alessandro. So one question is on global simulations. So do you have an idea, or is there future work planned to do more global simulations to see if including effects from the edge can help to recover some confinement improvement, particularly in spherical tokamaks?
Well, there's a quite number of global simulations now, especially done by Giovanni Di Giannatale at SPC, where with the Orb5 code, we see so global flux-driven simulations, we see that the negative triangularity outperforms positive triangularity. But yeah, these are simulations for the core, so they include only partially the very edge. And so it would be great to do also simulations, including also the sweep of layers. So like using codes like GNX, for example, would be really, really nice. So yes, it is planned.
I think Philip Ogle did some preliminary simulations along these lines, right?
As well. Okay, yes, thanks. Sorry, I forgot.
What about, are there any global simulations of spherical tokamaks for negative triangularity?
Not that I know about. But maybe I'm mistaken, but to my knowledge, I don't know.
Okay, and then there's a question about your database analysis. So yeah. You showed, I think, exclusively negative triangularity, but the question is, there's a big spread in the results in terms of, say, H vector. Is that spread comparable to PT, or is there somehow more uncertainty for negative triangularity or more variance in the results?
I never checked for TCV, so but I'd like to do it for sure. It's the next step. So to have the two plots and compare them and see how they exactly how they compare. So and also if we can, but for sure I want to reduce the spread. So actually those points were really taken quite. Yeah, we didn't pick specific shots. So for sure, if we consider more stationary shots and I don't know, we reduce and we select only shots with a certain fraction of radiated power and so on, for sure we can reduce the spread. So this was really a general picture.
Okay, thanks a lot, Alessandro. The final talk for today is Haley Wilson. Haley is a PhD student at Columbia University. Her PhD is focused on the integrated modeling of power plant scale tokamaks. And in particular, she's in the process of working with Oak Ridge National Lab using the FREDA framework on modeling large devices. So go ahead, Haley.
Thank you, Justin. Hi, everyone. I'm going to be talking to you today about Manta. So everything up to this point has been experimental work, and I get to take it and try and apply it to a fusion pilot plant concept. To start out, I just wanted to thank the members of the Manta collaboration, primarily people from both MIT and Columbia University working on this project. It's a whole device model, so there's a lot going on, and it couldn't have been done alone for sure. So this is review. I'm going to go quickly through this. Hopefully you have this down by now, that negative triangularity can help meet two main power handling goals for a fusion pilot plant. The first is to avoid type 1 ELMs. So this is just the figure that Oak showed, once again, as a reminder that once we're past this critical negative triangularity, we can operate robustly ELM-free. This is important because reactor class devices will likely not be able to tolerate ELMs. But at this ELM-free performance, we can also have comparable performance to positive triangularity H mode. The second thing is that it can help us integrate a diverter with a high performance core. How does it do this? It's because NT exhibits L mode-like pressure edges that can recover PT H mode-like core pressure. So that's shown in this plot, also from Oak, that is showing the pedestal pressure on the x-axis and the average pressure on the y-axis. So we see that even compared to these other small ELM, no ELM regimes on D3D, we have very high average pressure for a relatively low pedestal pressure. This allows us to utilize the fact that we don't have to maintain H mode to be able, so that we can lower the scrape-off layer power even further using, for example, something like seeded impurities. And also NT just has this benefit of a larger diverter wetted area just due to its geometry of the X points being at a larger R. So like I said, that's review. Hopefully you've gotten that at this point, but now let's try it. So in this Manta collaboration, we created a negative triangularity fusion pilot plant concept that meets all the requirements from the National Academy of Science, Engineering, and Medicine's report called Bringing Fusion to the US Grid. So this was created in a joint MIT-Columbia fusion design class. The NASM requirements were that the Q electric were greater than 1, it had a tritium breeding ratio of about 1 or higher, that the overnight cost was less than $5 billion, that the net electricity was greater than or equal to 50 megawatt electric peak for 3 hours, and that it could have operation through several environmental cycles. I will say that we did meet all of these. We also exceeded most of them. And additionally, it's able to operate with a simple diverter. So in this schematic here, you can see that is not a long leg diverter. It's not a snowflake diverter. It's a simple diverter. And there is a additional paper in addition to the original Manta paper specifically about the power handling of the diverter. The Manta core operating point was constrained by other aspects of the device. I have here 4 examples of that: separatrix density, scrape-off layer power, fusion power, and auxiliary power. So for example, these green constraints that we were within, the separatrix density and scrape-off layer power, were set by our diverter requirements. The fusion power was set both by having an upper limit set by neutronics, so that we did not sustain too much neutron damage to not be able to operate through several environmental cycles. Also by economics, because we needed to have sufficient gain in order to make this match the NASEM report requirements for overnight costs, and auxiliary power was additionally constrained by economics. Once again, just getting that gained fusion power over auxiliary power where we needed it to be. So as you can see, these final operating points that are indicated by stars on this plot show that we are within all of these constraints for our final operating point. And to compare to another high field fusion pilot plant concept, we have the original ARC design parameters on here. So as you can see, lower separatrix density, higher scrape off layer power, both due to the fact that it's operating in H mode and also due to this lower separatrix density, but with similar fusion power and similar auxiliary power. So we have a comparable gain to this other high field fusion pilot plant concept, where it is also of note that the ARC design had a predicted H factor of 1.8, whereas MANTA has an H factor of only 0.7. So you may be asking at this point, how was the MANTA core modeled? It was modeled using integrated modeling with the step code that is part of the OMFIT framework. It's basically a wrapper that allows data exchange between various OMFIT modules, so we are able to come up with a self-consistent solution between equilibrium, transport, heating, etc. So in this work, we used Procreate, Chef, Cheese, tgyro, and Baloo. Procreate was to initialize parameters. Chef was used as an intermediary between Toric, which is where we actually modeled the heating requirements for this, Toric with CQL3D. Cheese was used as our equilibrium code. tgyro was used for transport with TGLF for turbulence. And then Baloo was used to check the ballooning stability of the edge, which also at this point, you should know that that is important for analyzing these NT shots from previous talks. So tgyro, TGLF with SAT2 was able to converge the profiles out to rho equals 0.85. So I have those profiles shown here for reference. We did use seated krypton in this design, and that's to help radiate power at the scrape-off layer, as I mentioned. And it did not degrade the core performance significantly enough to make it so that we weren't getting the gain that we needed. I also have the heat sources on here in the bottom right, so you can see those auxiliary deposition profiles from Toric, also the fusion power contours and the line radiation from the seated krypton. The electron and ion temperature were evolved independently in this, just as a note. So this is out to rho equals 0.85. So what happened beyond rho equals 0.85? We were able to constrain this by a number of things. First, I'll talk about the temperature. So the temperature edge ended up being significantly below that of other positive triangularity, or not other, but of positive triangularity H-mode fusion pilot plant concepts. So first of all, this temperature profile had to be sustained by the 40 megawatts of input power. So if it was too high, it wouldn't converge. But this really just sets a first guess, which I'll talk about in a few slides, how we checked this first guess to make sure that it would make a feasible NT edge. We also found through doing scans of the temperature edge that the performance was heavily dependent on this value of temperature at rho equals 0.8. So this is a plot of these scans for a MANTA-like equilibrium. I also have the MANTA point on here as reference at the bottom. So we did these scans of the temperature edge and also the auxiliary power to see what would happen to fusion power. So there's also, we see from this plot, a space for optimizing maybe this NTFBP operating point. But we wanted to stay very conservative with MANTA to try and make sure that we weren't over predicting any performance in these simulations. So like I said, I will continue to talk about whether or not this temperature edge is feasible in a few slides. But first I'll talk about how we set the density. So the motivation for setting a higher density value is that higher separatrix density allows lower scrape-off layer power. And in NT, you can implement higher separatrix density values because there are smaller gradients in the negative triangularity edge. So you can raise up the separatrix density, and you don't have to additionally raise up the density at rho equals 0.8 or 0.85 or wherever that boundary condition is in order to sustain the H mode like gradients. So this is a plot from the diverter paper that spun off from the MANTA project, where QSurf is the maximum perpendicular heat flux density on the diverter targets. To have simple diverter integration, this number had to be less than 10 megawatts per meter squared, so that's denoted by the black dashed line on this plot. All of these points are converged simulations in UEdge, where the inner diverter leg was detached and the outer leg was attached. And choosing this separatrix density put a lower bound on edge density. So what we ended up choosing for MANTA was the separatrix density of 0.9, and we got a separatrix density of about 24 megawatts. Once again, this sets a first guess. So how do we make sure that this will actually be feasible in an NT edge? As talked about previously, we know that the NT edge cannot exceed the ballooning stability, the first stability boundary. So you've already seen a plot similar to this one on the right, and this is just serving as an upper limit for an ELM-free edge. We know that in NT, this ballooning, the second stability region, access to it is closed off by this ballooning unstable region. So we have the point at rho equals 0.85 that's set by core transport. We have the point at rho equals 1 that's set by the diverter. And this is where things get hairy because it's difficult to know in any regime, not just NT, what is happening in this edge region. So we interpolate an approximation. Try to match experiments on D3D to make the shape generally correct, and to see if we remain in that ballooning stable region, the first stability region. So we used a modified tanh function to do this. The blue lines on both correspond to the same pressure. So on the right, that's the normalized pressure gradient. As you can see, it's well below this instability limit. So we are more confident that this is an NT-like edge. Although, like I said, it's hard to be fully predictive because we don't have physics-based models for the edge region yet. Additionally, like I noted before, seeded noble gas impurities were used, specifically krypton in the MANTA case, but for these figures, they used neon to show the effect of this. And those are able to radiate power at the scrape-off layer to help the diverter integration. So MANTA used a radiative fraction of 0.8 with seeded krypton in order to reduce the scrape-off layer power. It's of note that highly radiative scenarios in negative triangularity have been established on D3D. Olivia Caselli did that work and had submitted it to the NT special issue for PPCF. So we do see in PT, there's been many experiments of the seeded impurities being able to raise core performance while simultaneously decreasing the scrape-off layer power. And so it's just of note that that has been experimentally shown in NT as well at this point. So I hope at this point that I've convinced you that the ELM-free negative triangularity regime has massive potential as a fusion pilot plant with simple diverter integration. And we demonstrated this with the MANTA FPP concept. So first of all, MANTA meets the requirements for a fusion pilot plant in the NASEM report. If you want to learn more about that and how the MANTA design accomplished that goal, you can read about that in a paper that was published in the NT special issue. Additionally, the high performance MANTA core is able to utilize an NT configuration and seeded impurities to integrate with a simple diverter. I've mentioned that paper already, but you can see that in this Miller et al. Paper also published in the NT special issue. And additionally, we've seen that there's potential for optimization in the negative triangularity fusion pilot plant space. If you want to learn more about that, I have a paper submitted that hopefully will be published soon and that I've linked the archive for in the next slide that I will pull up. The future work priorities are to develop a physics-based predictive model for the NT edge so that we can be more confident in the extrapolation into that region, and also to do more whole device modeling for new operating points. There are a few new whole device modeling tools that are coming out, like Justin mentioned in my introduction. I am going to start working with one of these, Frida, in the coming months, which is very exciting. So I mentioned all these papers, but here's QR codes if you want to scan them and read more about this work. And with that, I will take any questions you have.
Thanks. So maybe the first question. So you you gave at the beginning of your talk the H factor, I believe, for Manta, which was like 0.7 or 0.8. Is that an input or an output of
It's an output.
your design study? Okay, and so how do, from the results presented by Alessandro on TCV as well as Oka on D3D, it seems like 0.7 or 0.8 is on the low end, but maybe more in line with the JET results. I mean, should we see this as something that's conservative, or is this telling us something about the scaling with size?
Yeah, I definitely think we should see this as something that's conservative. Obviously, it's hard to know until we actually make a device this scale, if these things are going to hold out. But yeah, like I said, in the Manta design, we specifically tried to be very conservative to show that this was still feasible, and that we weren't taking any anything that we shouldn't be taking in terms of performance.
Okay, another question is on drawbacks of negative triangularity in your design process. Are there, for example, the MHT stability limits that you have to, somehow compensate for in your optimization?
Absolutely. Yeah, so one of the primary things that NT faces as a stability limit that there is also a paper on by Sofia Guizzo is the vertical stability. So that is something that constrained us in this configuration. We also tried to be very conservative with it. So this is a very short elongation relatively. Additionally, we had to push out to larger major radius than, for example, in the ARC project. But this did allow us to make a bigger central solenoid, so we could have longer pulses, which was helpful to the design. So it was a trade-off we had to make, but that ended up being beneficial in the end. And yeah, we tried. I showed the ballooning stability in the edge. Like I said, we tried to be really conservative with our edge predictions to make sure we weren't predicting performance that we shouldn't be.
Do you have a feeling for how the H factor depends on that assumption? If you were a bit more aggressive in your prediction, does that actually have a substantial effect on H?
I do. I have a backup slide actually that can show this. I think.
So we can't currently see the slides, but maybe.
Oh, okay.
If you could summarize it verbally.
That's okay. So in the paper that I referenced, that is my paper, we did this scan. Can you see this? Of the
yes, we see it now.
Edge and the temperature edge and its effect on H factor. So if we had pushed the Manta edge higher, which isn't necessarily, it would match experiment actually to push it higher as well. But like I said, we were trying to be very conservative. But if you push it higher, you do get to these higher H factors, as you can see in this plot. So that top right region, it does go ballooning unstable, however, but you do get those higher H factors. So there's optimization to be done there.
And a question I had is there a similar positive triangularity design that was focused on similar targets that we can use kind of as a comparison?
Yeah, this is a good question. There have been, I mean, there are obviously many positive triangularity designs of reactors, but I think probably a good comparison would be to the previous iteration of this design class, which made ARCH, which was a radiative L mode positive triangularity fusion pilot plant. So that one would have similar, it should have similar power handling and performance, but be in positive triangularity H mode. And then obviously I brought up ARC as a comparison just as a benchmark to test other fusion pilot plant, high field fusion pilot plants against.
Okay, thank you very much, Haley. No more questions. So now we turn to the final portion of today's webinar, which is a panel discussion. So if I can ask all of the past speakers to turn on their webcams. So there were a couple of questions that came in through the different talks that seemed quite general, and so I think it's good to have multiple perspectives on them. So the one thing that wasn't really addressed too much today was on scrape-off layer transport, and so from an experimental perspective or a theoretical perspective, what do we know about scrape-off layer dynamics and negative triangularity?
It's a great question. Maybe I can start with some insights from D3D. So if you remember from the D3D presentation, the scrape-off layer is not very well optimized in the character or in the configuration that we have. We have very small strike lines and not too much variation. We hope to improve that with future upgrades, but even with that small strike line and relatively constrained configuration, we're able to see some things going on. One important aspect of that work is access to detachment, which of course we think we need in a reactor. The D3D plasmas were able to access detachment, and you can see that done in a variety of different configurations. Generally, we need slightly more density to access detachment than you need in positive triangularity. This could be solely a result of the short connection length rather than necessarily a function of NT itself. Future work needs to be done there. I think another big question that always pops up here is the heat flux width, which is an ongoing area of research. I think at many tokamaks and people at TCP, et cetera, can help add in some context here. What we've seen on D3D is generally negative triangularity heat flux width is a bit broader than it would be in a type 1 ELMi H mode scenario, but a bit narrower than it might be in a positive L mode scenario, so somewhere in between. And it can approach the width that you'd seen sort of inter-ELM in ELMi scenarios. This does need further study and extrapolation and exploration, both of modeling and experiment, but that's what we've seen so far from the data.
Any comment from TCV?
Yes, we see similar things. We see that it's quite difficult to detach, so there's a significant study on that side. Even just having the top triangularity being negative and a standard X points, we also have difficulty to detach, and this is being studied with various parts. You have a recent paper also in the special issue, also one from D3D, so you can see the differences. The same is seen for the land accu. What is also seen is that there is an improved transport, so lower turbulence in negative triangularity in the scrape-off layer as well. So that's a study from a PhD student from SPC. So yeah, it goes together. One recent development that you will probably see next year in a paper from TCV is that we combine a snowflake diverter with a top negative triangularity, and we reach very high beta n, also around 2, and keeping the snowflake down and then studying the exhaust. So that's the next studies.
Good to have something to look forward to. So the big question I had, I wanted to actually start the question by summarizing the experiments of negative triangularity that I'm aware of. So, you know, we've heard a lot about all of the shots on TCV. There's been a good number on D3D, some on ASDEX, now a handful on JET, and one on MASTU at least. We also know there's a spherical tokamak under construction in Spain called SMART that will have the capacity to do negative triangularity. And also just yesterday, I heard that there's a tokamak in China, a spherical tokamak in China called Sonus 2 that has performed some negative triangularity shots. And this is a fairly significantly sized spherical tokamak. Of course, none of these devices are designed for negative triangularity, right? So TCV is kind of neutral, but the rest are really targeting positive triangularity. And so do we need in the community a negative triangularity device, or really a dedicated, specifically optimized device for negative triangularity? And if we need it, what should it look like? What size, what aspect ratio?
Maybe I can say something. I mean, if you're asked, do we need something like this, then of course the answer is yes. Let's build one. The question is, who does it and who pays for it? But I think, yeah, I think that there would be reason to do it. But I think also that we can still do some studies on the plasmas we have, and we have now a plethora of new results which could still help us assessing better the performance and what we would expect. So one example is, and I try to touch upon this in my talk, there's this wide variation in pedestal top heights. And these impact the performance. And I think also Haley talked about this. And to have physics understanding there, I think would be very helpful. Maybe only a new machine could give us that. But I think with this large variation Oak has in this database and the codes coming up that are able to simulate from the pedestal top to the scrape-off layer, there might be still something we can learn in the next 2 or 3 or 4 years to make a more informed decision of which parameters this new machine should have. My opinion.
I guess I can add some.
Yes, please.
There as well. I fully agree with Tim. I think everything he said is exactly correct. I'd add on that looking forward at new machines that are being built. So this is the next generation of machines like ITER, like Spark. It'll be even more difficult to make negative triangularity shapes on those machines than it will be in our present day machines. So while there's certainly a lot we can learn with our existing machines and improving and comparing databases, like Tim said, I think an excellent place for a new negative triangularity device would be somewhere that can access these burning plasma regimes so that we can study those effects in NT as well.
Maybe I could just, at the International Spherical Torus Workshop, we heard that there are plans in China to build a dedicated negative triangularity spherical tokamak. So that means that the toroidal field cores will be, pointed in that direction in the vacuum vessel as well. So that'll be very interesting to have a dedicated device if it happens. But this is related to a question to perhaps all of you. We know that disruptions can be a bit more of an issue in plasmas which have negative triangularity. Is one of the potential reasons for that the clearance between the last closed flux surface and the vacuum vessel, or the wall rather, is it because the clearance is larger? Is that part of the issue here? And therefore, will a dedicated negative triangularity device help in that respect?
I was actually going to bring that up in reference to Sofia Guizo's paper on vertical stability, at least specifically. Vertical disruption events could be better mitigated by having like a conformal vessel wall or things that you would have to build to specifically be on an NT plasma instead of putting an NT plasma in a PT device.
I think we might be biased by our present machines because it's not so easy to control vertically. The negative triangularity has always the larger n equals 0 growth rate and has a lower coupling to the wall actually. So we need to be closer, but we don't have walls to be close. And so we navigate in a domain where, okay, with the operation we can do, this was mentioned, we try low kappa because we have some constraints. Or in TCV, we can do not as well as, well, we don't do as well as maybe 15, 20 years ago in terms of beta, because we are in the middle of the chamber instead of near the top, because our NBI hitting in the middle. So we might study regions which are not yet at the optimum, for example, for elongation, because we don't have a proper machine. And the other part is that we tend to do campaigns in between campaigns for positive triangularity. So we don't do, for the positive triangularity, we nevertheless optimize our knowledge. Of course, we have cores and that's good, but our knowledge of experimental studies is over tens of years, is not over tens of weeks. So if we have a dedicated machine, not only it will be designed to perform well, but also we will have a dedicated team to make it perform well, and we will discover new things. And that's I think what we are missing now.
Thanks. A question maybe most targeted at Haley is looking forwards at a power plant. What are our current blind spots? What are the biggest risks? What are the things that need de-risking for negative triangularity, obviously?
One of the big ones that comes to mind is that the MANTA work didn't do any modeling with respect to disruption. So like we were just talking about, that NT likely will have more disruptions. And so that is like a limitation of that work specifically. In general, it's just actually scaling to these reactor levels. Like if we know that, we don't know if we're going to see the same physics yet, but that's a problem for every regime. But more dedicated experiments to specifically the edge region seems to be what is most interesting about NT. And so to have a like physics-based predictive model of that edge, I think would help a lot, and is like a current like huge uncertainty in determining performance for an NT reactor. Those are the things I'd bring up.
Has there been any work on designing negative triangularity magnets?
In the design class, we did try doing negative triangularity magnets. We ended up choosing to just do, like as you saw in the Manta design, it was just like these elliptical, almost elliptical, but just rounded corner window frame magnets. We basically didn't see a huge benefit to doing NT magnets, and it actually puts a lot of stress on the far corners if you try and make the NT shape. So we decided to abandon it and do those window frame shapes. And additionally, Columbia is doing another design class for a smaller, cheaper, not tritium breeding NT tokamak, and they have come to a similar conclusion that doesn't seem worth the stress. But that's just
even for magnets without joints in them.
Yes, yeah, the biggest areas of, at least from a stress standpoint, of that are problems are those corners where it becomes a D, and so those there wasn't a significant benefit from doing that. I think a benefit that could come is just having more space on the inboard side, but you only need to make the inside curved for that, and then you might as well make the outside curved as well and not make it a corner. And then you have more room for the diverter out there too. So that was just.
Interesting. A question maybe for Alessandro. So given the dependence on turbulent regimes, so is it likely that the ideal heating mix for negative triangularity will differ from what we think about for positive triangularity?
I'm not sure. I mean, for sure, according to my simulations, you want ITGs, but potentially in fusion power plants, ITGs are supposed to be the dominant type of instabilities anyway. So maybe it's a good news, but yeah, I mean, I'd say we want ITGs, and I don't know if this could potentially change a lot the heating mix that we have in mind already.
Just quickly, I mean, if you really have a power plant, then you're not really you can't really decide what the plasma does in the end. I mean, there will be the alphas and they will heat the electrons. The only thing which you need to take care of is to bring it into a burning condition. But then the electrons will be heated, and you're, of course, to the coupling, you will heat the ions. So I guess if the density is high enough, then it should be fine.
Another question for the panel is it only the pedestal that you care about when it comes to infinite end ballooning? If you increase beta, does the core stay ballooning stable?
That's a good question. Certainly, most of the work we've focused on is focused on the edge, because one of the best things with negative triangularity is it's elm-free, and we've tried hard to explain why that might be. There is work modeling, for example, the core region of spherical tokamaks that sees the ballooning limit playing a role in negative triangularity situations for reactors, even farther into the core. So far in work we've done for Manta and other conventional aspect ratio extrapolations to FPPs, it does not seem like the ballooning limit will play a stability role in the core. Rather, you'll be limited by transport throughout the core region. But I think one of the key points here again is that NT plasmas are not necessarily a monolith, and that there may be different regimes limited by different things. So that certainly deserves further exploration.
When you do the design for the tokamak, I remember even the TCV calculations. The paper is 1988, if you want to look. And if you do the same now with NT, you will see that's the pressure profile at the first ballooning limit in the core will bring you to a beta n, which is much higher than the global n=1 limit. So usually it's actually the n=1 which is limiting you for the core part. So yeah, that's fine.
Maybe I'll just make a comment that it might depend on the magnetic shear. So there are, when we go to spherical tokamaks in particular, they're looking at a minimum of, well, looking forward towards, well, mass due and then towards future, the STEP device, for example, the spherical tokamak that's being developed for a fusion power plant in the UK. The Q min, the minimum value of Q is just above 2, and there'll be a region of relatively weak shear in the core. And there you are interested in infernal type modes, and these are low end ballooning modes, these types of modes, and these are impacted by a negative triangularity if you were to go to a negative triangularity shaped device. But again, this may not be a bad thing, right? We do sometimes want these instabilities to be more unstable in certain situations, just like we do for the ELMs. So that's
yes, these tend to be more local, so more like sawtooth effects. And
yeah.
All right, so have there been studies to try and predict turbulent transport at high fields in negative triangularity configurations? And I'm going to add on a bit of, is there a particular synergy of lack of synergy between, for example, the HTS magnet development and negative triangularity?
I can comment briefly here. The MANTA studies are quite high field. And you can see some basic transport predictions there, although it's not first principles gyrokinetics from the beginning. There's also a study from PPPL looking at more 0D scalings in scaling magnetic field and in triangularity as well. And what they find is actually a strong synergy between high B and MT, where negative triangularity can actually take better advantage of high magnetic fields than positive triangularity can in some circumstances. I think it's still preliminary, and we do need some first principles simulations going forward. But at least from the onset, it looks like there's an expanded benefit of high B in MT.
I mean, I guess we can say in the context of gyrokinetic simulations, or at least local gyrokinetic simulations, that the magnetic field basically gets normalized out. And so, you know, you get this gyro bomb scaling, and you actually can't really do a particularly exciting scan in magnetic field for gyrokinetic simulations, but it's kind of baked into the normalization. All right, there's one question that I don't think we've touched on, which is impurity transport. So there was a specific question for Tim actually during your talk about, is there an issue with tungsten accumulation when you don't have ELMs anymore?
In these plasmas, we didn't have specific problems with tungsten accumulation. We usually used some ECRH in the center, which usually is our recipe to avoid tungsten accumulation. Having said that, the problems usually come up when we have H modes and with low frequency ELMs, and then the impurities are sucked in. This is just what I think is that due to the fact that we are in a more ELMOD-like situation with stronger gradients, we do have just transport of the impurities, and we don't run into these problems. This is actually, in the past, I worked on I-mode, and this is also the case there, that we never had troubles with impurity accumulation in these kinds of regimes.
Isn't it in part because the density gradients tend to be a bit flatter than compared to H mode, and the temperature gradient's a bit steeper, and this is excellent for preventing impurity accumulation, isn't it? This is the conditions that you want.
You mean temperature screening?
Yeah, exactly. So you tend to have relatively good temperature gradients and fairly weaker density gradients compared to H mode, and that's preferential for preventing impurity.
That's preferential. However, in temperature screening, I think this gradient T term has to take over at some point, and for that you need quite a difference. So you need rather strong gradients, and I don't think this is the case here. But I haven't calculated this, I have to say.
I'll mention briefly that there are two big studies of D3D transport in D3D, which are done by David Eldon and Olivier Casali. Both of those are under review right now, but should be part of the PPCF special issue shortly. So to check those out when they come out.
Maybe I just wanted to add that I did a few gyrokinetic simulations on changing carbon and tungsten and do artificial scans, and I didn't see any big difference from, let's say, macroturbulence point of view. Like NT and PT were behaving quite similarly.
Maybe I can ask a question to all of you. I'm not sure if Justin has gone, but oh, yeah, you're there. Could I ask, so quite a few of you, you presented JET experiments and Aztecs upgrade and D3D. And what we see there is when we try to get negative triangularity, the main triangularity is usually at the top, and it's difficult to make negative triangularity near the X point. And what that means then is that you end up with a slightly twisted configuration in the cross section. So that means it's up-down asymmetric. So do we need to consider the effects of up-down asymmetry in our calculations, and is that as important perhaps as the negative triangularity as compared to positive triangularity? I think, Justin, you've done some work on up-down asymmetry in the past, haven't you? So I wonder,
yeah, I mean,
it seems to be like an area of research which is a little bit under-investigated. So should we be looking at this more carefully? And is it something that we explored in TCV as well? Because of course in TCV you might be able to play around with the up-down asymmetry.
Yeah, I can definitely chime in. I mean, the interesting thing, in my opinion, is once you start breaking up down asymmetry, then you start to drive intrinsic rotation, which can have important impact, as we know, and generally a positive impact. The other interesting thing is related to what Tim had said in his talk, which is you kind of get this almost fictitious triangularity that stems from the way that we define experimentally triangularity. And so, one broader question is, do we have to be careful about just sticking to this one definition of triangularity, and are there things that we're missing and potentially, might cause a blind spot if we don't come to a deeper understanding of the effect of the whole plasma shape rather than just this one parameter delta?
Perhaps worth saying that a lot of codes assume up-down symmetry. So maybe equilibrium, not all even equilibrium codes include this, but most do, like EFIT and so on. But most stability codes and then most gyrokinetic codes that sit on top of those equilibria, they usually have an assumption about up-down symmetry. So this is perhaps an area that has not been deeply investigated. I may be wrong, but it's perhaps something that we should all be looking at a bit more. What you did, Justin, was an exception, I think, for different applications.
Okay, thank you very much. I think it's now time to officially close this webinar. So I want to say that for those who are interested in revisiting it or sharing it potentially with colleagues, on the west coast of the US, for example, a recording will be made available. So this will be emailed out to all the participants. I would like to thank, of course, the organizers from PPCF, Lucy, Ian, John, as well as all of our speakers. You did a very good job and I think communicated things quite clearly. And to the audience, thank you for attending and I hope that you found it valuable. Thank you.
Thank you, everybody.
Bye.